Welcome to The Explainer. All right, let's talk about Saturn. We all know the rings, the moons, but it also has a couple of really big puzzles that have stumped scientists for years. Today, we're going to dig into one theorist's attempt to solve both of them with a single, really elegant idea.
So puzzle number one is its magnetic field. I mean, you look at its big brother Jupiter, and then you look at Saturn, and something's just off. Based on its size, its spin, all the things we know, its magnetism is about 3 times weaker than all the physics says it should be. Why?
And then, of course, you've got the rings. For decades, we've seen these weird, ghostly spokes that just show up, dance around the rings for a bit, and then, poof, they vanish. What on earth are they, and why don't they stick around?
Now, mainstream science has a few different ideas for each of these puzzles. But today, we're exploring a fascinating alternative view from physicist Miles Mathis. His claim? That these two things aren't unrelated at all. In fact, they're connected by one single foundational idea.
Okay, so let's dive right in. To really get our heads around this, we need to start with the big idea at the center of it all, a universal charge field. Basically, the idea that space isn't empty.
So according to this theory, space is absolutely teeming with activity. It's a dense sea of these tiny, spinning charged particles. And this isn't just some random background noise. No, this field is what's actually driving the physics of the entire solar system.
So what's the deal with these particles? Well, it's pretty simple, really. It all comes down to their spin. You've got photons spinning one way and antiphotons spinning the opposite way. And the key thing to remember is that the mix isn't the same everywhere. The further you get from the sun, the more antiphotons you find in the mix.
And this is where it gets really cool. Every planet in this view acts like a giant charge engine. Its rotation creates this amazing system where it's constantly sucking in this charge field at its poles and then whipping it back out at the equator thanks to centrifugal force. It's a non-stop recycling system.
Okay, so we've got this idea of a charge engine. How in the world does that help explain Saturn's mysteriously weak magnetic field? Let's connect the dots.
Let's really put this into perspective, right? Based on all the math, scientists figured Saturn's magnetism should be about 1/3 of Jupiter's. Makes sense. But what we actually measure, it's way, way less, more like 1/9 of Jupiter's. So we're left with this mystery factor of 3. Where did that strength go?
The first piece of the puzzle is that balance between photons and antiphotons we just talked about. I mean, think about it. If you had a perfect 50-50 mix, all those opposite spins would just cancel each other out completely. No net magnetic effect. So it follows that the more balanced the field is, the weaker the magnetism is going to be.
So the author crunched the numbers. Jupiter is in a part of space with a certain imbalance of these particles. But Saturn, being way farther out, is in a region that's much more balanced. And that difference alone, just the change in the mix of particles, accounts for the first 1.5 times reduction in magnetic strength.
The second factor? Well, it's actually way simpler. It's just density. You know how there's more sunlight the closer you are to the sun? This theory says the same is true for this charge field. Jupiter is just cruising through a much thicker soup of these particles than Saturn is.
So does that density really matter? Oh yeah. The calculation shows that because of that difference, Jupiter is grabbing about twice as much charge as Saturn is. And that gives us our second multiplier.
Okay, and this is where it all just clicks into place. You take that 1.5 times difference from the field times balance, and you multiply it by the 2 times difference from the field density. And what do you get? You get exactly 3. Boom. The theory says that's the reason for the threefold weakness. It's not one thing, it's 2 separate factors working together.
All right, that's one mystery down, one to go. So, how does this exact same theory explain those ghostly spokes in the rings? I mean, it seems like a totally different problem, right? Well, it turns out the explanation comes from the very same set of principles.
So the author just flips the whole question on its head. He says, look, the real mystery isn't why Saturn has spokes. If planets are constantly shooting out charge from their equators, like we said, then spokes should be happening all the time. The real question is, why are Saturns so faint, and why do they keep disappearing?
And the answer, according to this theory, comes down to how lumpy a planet is on the inside. A rocky planet like Earth, super lumpy, right? You've got mountains and oceans and a dense core. It would shoot out charge unevenly, creating these big, obvious, permanent spokes. But Saturn's a gas giant. It's way, way smoother. So its charge flow is much more even, leading to these faint, barely there spokes.
Okay, but why do they come and go? This is where it gets really clever. The theory links it to the sun's own cycle. So when the sun enters a solar minimum, a quiet period, its own charge field weakens and becomes more balanced. This change actually stirs up Saturn's outer gaseous layers, making them even smoother than they normally are. And when that charge emission gets super even, the spokes just fade away.
All right, so let's pull back for a second and just look at the big picture this theory is painting for us.
The main takeaway here is pretty amazing when you think about it. You have one single idea, this universal charge field, and it's being used to build a cohesive explanation for two completely different cosmic mysteries. The weak magnetism is all about Saturn's place in that field, while the spokes are all about how Saturn interacts with that field.
And that leaves us with a really big question to chew on. This whole model uses just a few simple rules to tackle these huge, complex, long-standing problems. So whether it's ultimately proven right or wrong, it makes you wonder, doesn't it? When does a simple idea stop being just a model and become a truly powerful explanation for how the universe actually works?